So our next speaker is Nima Hoda, who's going to speak a bit about constructing bisimplices.
Okay, yeah, thanks. Thanks for the invitation to speak again. Yeah, so bisimplices are a family of cells that can be used to give higher dimensional skeletons to bipartite graphs. They're appropriate for certain families of bipartite graphs. My own motivation was in giving higher dimensional skeletons to a family of two-dimensional square complexes called quadric complexes, which are kind of type of combinatorially non-positively curved complexes. They generalize cat-zero square complexes, and they're analogous in many ways to systolic complexes. If you're familiar with those, those are complexes that have seen quite a lot of study in geometric group theory for their non-positive curvature-like properties. So, the main use that I found for bisimplices was the following theorem: that if you span a bisimplex, which I'll define soon, on each complete bipartite subgraph of a quadric complex, where the parts have at least two vertices, then the result is a contractible complex with the same two skeleton. And this actually holds for the class of all locally finite bidismantlable bipartite graphs, which is a much larger class of graphs. Bidismantlability is a kind of combinatorial contracting property. And in particular, the theorem also applies to absolute bipartite retracts, which are kind of bipartite analog of heligraphs, which heligraphs have seen a lot of activity in geometric group theory in recent years. So what's a bisimplex? The definition is inductive. Start with 1-1 bisimplex. It's just a square with the usual cell structure. The one skeleton is K22, complete bipartite graph. And in general, an MN bisimplex with M and N least 1 is obtained by starting with a Kn plus 1, N plus 1 complete bipartite graph, and then spanning a bisimplex on each proper complete bipartite subgraph, having at least two vertices in each part. That gives us what we call the boundary of the MN bisimplex. And then we take the resulting sphere of dimension n plus n minus 1, and we plug it with a cell of dimension n plus n. And that's how we construct bisimplices. So the 1-2 bisimplex case is depicted above. Start with a complete bipartite graph K23. It's got 3 K22 subgraphs, so 3 4 cycles. We glue in a square, which is the 1-1 bisimplex, to each of those subgraphs. So that's sort of 2 squares in front and 1 square on the back, so to speak, in this middle picture. That gives you a sphere of dimension 2. And if we plug that with a cell of dimension 3, we get a regular CLV complex homeomorphic to the 3 ball, and that's the 1-2 bisimplex. So you can compare this to the case of simplices. So if you have a n simplex, its one skeleton is a complete graph, Kn plus 1. And its cells are in correspondence with its complete subgraphs. So it's very sort of analogous idea. But you might have noticed that there's a problem with this definition, or there's a, it sort of begs the question, how do we know once we've glued in all the lower dimensional bisimplices that what we get is actually a sphere? And that's what the rest of the talk is about. So that's the main difficulty in defining bisimplices, is proving that in this inductive step, what we get is actually a sphere. So one of the tools we're going to use to prove that it is in fact a sphere is discrete Morse theory of Forman and Forman's sphere theorem. Start by setting up what kind of cell complexes we're talking about here. For this talk, that's going to mean a regular CW complex. CW complex is regular if its attaching maps are all embeddings. So, for example, a graph with a loop is not a regular CW complex because the attaching map of the loop edge is not an embedding, but you could have a bygone, say, in a regular CW complex, because both those edges, they still have embedded, they're still embedded. So Forman Morse theory can be defined in terms of Morse functions, numerical functions, but particularly clean way of expressing the theory is using what are called Morse matchings. So Morse matching on a cell complex is a collection of pairs of cells, sigma I, tau I. These are ordered pairs. I'm depicting them as an arrow between two cells. I'm denoting them that way. Satisfying three conditions. So the first condition is that sigma I is a codimension 1 cell of tau I. So sigma I is contained in tau I, and it has dimension 1 less than tau I. That codimension 1 condition I'm going to denote by sigma I less than tau I with this particular less than symbol. That's the first condition. Second condition is that each cell appears in at most one pair. So cells don't have to appear in pairs, but if they appear, it should be at most once. So if a cell appears on the left-hand side of a pair, it shouldn't appear anywhere else on the left or right of any other pair. And also if it appears on the right-hand side of a pair. And the last condition, the sort of acyclicity condition, is that there are no sort of chains of cells, closed chains of cells of the following kinds. You start with a cell, you follow a matching pair arrow, then you descend down to a codimension 1 cell, then you follow a matching arrow, then you descend down to a codimension 1 cell, and so on. There shouldn't be any such chain of cells that's closed. That shouldn't exist. Finally, a critical cell of a Morse matching is a cell that doesn't appear in any pair. Okay, so let's look at a few examples, non-examples first. So in these cases, X is a triangle with its usual cell structure. So on the left here, we have a vertex that's matched with a triangle, and that's not allowed because things should be matched with something of a single dimension higher. The second example here is not a Morse matching because we have a vertex that's matched with two different edges. It's not a matching. That's also the problem with the third case, where we have a triangle that's matched with two edges. And in the last case here, we have a cycle. So we violate the third condition. So that's a vertex, and then we're following a matching edge. Now we're going down to a face of one lower dimension, and we're following a matching edge, and so on. And then we close into a cycle. So that's not allowed. And at the bottom here, we have a few examples of things that are Morse matchings. The critical cells are indicated in blue. So on the left, we have a single critical cell, it's a vertex. On the right, we have 3 critical cells, an edge, and 2 vertices. And it kind of looks like the Morse matching here is giving us a collapsing strategy down to the critical cells, and that's actually the case. And theorem of Forman's that if the union of the interiors of the critical cells, or the relative interiors of the critical cells, forms a subcomplex, then X collapses onto that subcomplex. Another theorem of Forman's is that if you have a Morse matching, then your complex is homotopy equivalent to a CW complex with the same number of cells of dimension D as there are critical cells of dimension D for every D. And finally, and most importantly for us, is Forman's sphere theorem. If you have a Morse matching with 2 critical cells, then your complex is homotopy equivalent to a sphere. And the dimension of the sphere is the dimension of the higher dimension of the 2 critical cells. Okay, so here's an example of a Morse matching with 2 critical cells. This is the boundary of the 1-1 bisimplex, and the matching is indicated with the arrows. And we have exactly 2 critical cells. We have the vertex E and the square ABCD. So that's a proof that the boundary of the 1-1 bisimplex is homotopy equivalent to the 2 sphere. But of course, we can actually just see that it's homeomorphic to the 2 sphere. Okay, and it turns out we can define, we can describe Morse matchings with 2 critical cells for the boundary of the MN bisimplex at this sort of inductive, at this state, this inductive step part of our construction of bisimplices. But that's not enough, right? We need to know that it's actually homeomorphic to a sphere, not just that it's homotopy equivalent to a sphere. Well, luckily we have the generalized Poincare conjecture, which tells us that it suffices now to show that the boundary of the bisimplex is a manifold. Well, how are we going to do that? In the case of a polyhedral complex, you would check that links of vertices are spheres. But we don't have a polyhedral complex here. How do we do that here? Well, we have to talk about links in general cell complexes or in regular CLV complexes. So if X is a cell complex, we consider the barycentric subdivision of X viewed as a directed simplicial complex. So what I mean is take the barycentric subdivision, it's a simplicial complex, and then we direct edges from higher dimensional barycenter to lower dimensional barycenter. Here are 2 examples. Example on the left, our initial complex is just the 2x2 grid of squares. And after taking the directed, barycentric subdivision, this is what we get. Example on the right is 2 squares that are glued together along a path of length 2 in their boundaries. This is the barycentric subdivision. And we're going to consider certain subcomplexes of the simplicial links of vertices in these barycentric subdivisions, the incoming links and the outgoing links. So the incoming link is the subcomplex of the link of a vertex corresponding to incoming edges. And similarly, we define the outgoing link. And you'll note that the outgoing link corresponds to boundaries of cells of X, and the incoming link corresponds to links. So our hope is to define a cell structure on the incoming link that's compatible with the cell structure on X. So if so that's exactly how we define things. We say that if the incoming link of a cell is the barycentric subdivision of some cell complex, then we say that that cell complex is the link of sigma. And it turns out that that happens precisely when the outgoing links inside of the incoming link are all homeomorphic to spheres. And if the link of every cell exists in X, then we say that X has links. That's the definition. Let's think about this a little bit more. How would you think about constructing the link? Well, we do it by merging cells, right? We have something that we hope is the barycentric subdivision of a cell complex, and we merge appropriate cells. Well, we merge things corresponding to outgoing links. And we do that inductively on skeletons. So we start with the things that don't have any outgoing edges, and those correspond to vertices of the link. And then we go step by step. We look at an outgoing link in the next higher dimension, and what we need is that the boundary, which is the merged outgoing link, is homeomorphic to a sphere. So consider the case where we're looking in the link of sigma, and we have a potential cell tau. We've got its boundary, and we have to ensure that that boundary is homeomorphic to a sphere. Well, the boundary of that cell tau is the link of sigma in the boundary of the cell rho that corresponds to tau. Okay. So if tau is the cell we want to build in the link of sigma, it corresponds to some cell of X rho, and the thing we need is that the boundary of tau is a sphere that's the same as the link of sigma in the boundary of rho existing and being homeomorphic to a sphere. And that's a sufficient and necessary condition for us to be able to plug tau there. And so for X to have links, it's a sufficient necessary condition that for every cell rho of X, the links of the cells of the boundary of rho exist and are homeomorphic to spheres. And it's a fact that if X has links, then the links of simplices of the barycentric subdivision of X are joins of incoming links and outgoing links. Well, the outgoing links are barycentric subdivisions of boundaries of cells of X. So if X has spherical links, and the incoming links are also homeomorphic to spheres, then the links of the barycentric subdivision are all spheres. So the barycentric subdivision is a PL manifold, and in particular, X itself is a manifold. Okay, why don't we always have links? It has to do with these things called homology spheres, but I'll skip over that. Okay, so that brings us to the sphere recognition theorem, which gives us our complete way to prove that boundaries and bisimplices are in fact spheres as we construct them. So the theorem says that if X is a cell complex with links, and it has a Morse matching with two critical cells, and every link of X has a Morse matching with two critical cells, then X is homeomorphic to a sphere. And it turns out that we can, in fact, define such a Morse matching on the boundary of the bisimplex. And we can do it for all the links as well. So this theorem is all we need to complete our construction of bisimplices. So here's what the matching looks like. I'll just briefly show that for the curious, but we'll skip over that. So how do we prove the sphere recognition theorem? By Forman's sphere theorem, the cell complex X is homotopy equivalent to a sphere because it has a Morse matching with two critical cells. And we proceed by induction for the rest of the proof. If X has dimension 0, then it's a discrete space. So it's a zero-dimensional manifold, so it has to be a sphere. If the dimension is greater than 0, then by the generalized Poincare conjecture, it suffices just to show that X is a manifold. Now for a, so we know that in order to do that, we just have to show that links of cells are homeomorphic to spheres. So let's take a cell sigma, and let's consider its link. We know by assumption that the link of sigma has a Morse matching with two critical cells. We'd like to show that the link of sigma satisfies the conditions of the theorem. So we want to also know that links of its cells have Morse matchings with two critical cells. Well, and also that links exist, first of all. And then we can, and then we're done by induction. So let tau be a cell of the link of sigma. Tau corresponds to some cell rho of X. And it turns out that the incoming link of tau taken inside of the link of sigma is isomorphic to the incoming link of rho taken inside of X. That's just, if you think about it, it's all the cells, it's the structure on all the cells that contain tau. Well, the cells that contain tau inside of the link of sigma are exactly the cell, the set of cells correspond to the set of cells that contain rho inside of X. So that tells us that the link of tau exists because links exist in X. And also that it has a Morse matching with two critical cells because it's isomorphic to the link of a cell of X. And so then the link of sigma satisfies all the conditions of the theorem. It has lower dimension, so by induction, we see that the link of sigma is indeed homeomorphic to a sphere, and so X is a manifold. So that's all.
All right, thank you very much. Does anybody have any questions in the audience? You can unmute yourself too. Can you speak a little more on the gap that was left just with the existence of the links? There was a couple before, right? It was this fact. It was right there. The two forward. Sorry.
Right. So this is how we go from links being spherical and X being a manifold. It's via the barycentric subdivision. So if the links in if X has links and they're spherical, then that's enough to show that the barycentric subdivision, simplices of the barycentric subdivision are homeomorphic to spheres. And the reason is because links in the barycentric subdivision are joins of incoming links and outgoing links. And I can give a little example of that. So we could look, say over here. If we consider the link of the cell sigma. Actually, I just realized now that I didn't describe what this is properly. This is actually two triangles joined at a single edge. And
Okay.
and if we take the barycentric subdivision, the incoming link of sigma is these two red barycenters that we have over here. And if we want the link of this vertex inside the barycentric subdivision, it's actually a 4-cycle, right? It's the join of the outgoing link, like the outgoing arrows, and the incoming link, the incoming arrows. And so that goes, you know, and it, because the outgoing link corresponds to the boundary of the cell whose barycenter we're considering, that's always homeomorphic to a sphere. And so if the link is the join of a sphere and a sphere, then it's going to be a sphere. So.
Sam, you have a question?
Yeah, at the beginning of the talk, you were talking a bit about non-positive curvature. So are there natural situations where you can put metrics on these bisimplices in some natural non-positively curved type way?
Yeah, I think probably not. Just by analogy to systolic complexes, the natural thing to do in systolic complexes is to deal with things very combinatorially. And so, and if you take a systolic complex with its simplicial structure, if you make the simplices just the Euclidean simplices, regular Euclidean you won't get a non-positively curved space. And so yeah, I think this is more of a combinatorial thing than it is a metric thing. It's, you know, I could be wrong. Okay. Maybe there's some way to do it. I would point out that these things aren't polyhedra, so you know you'll have a harder time metrizing them than just choosing how to, you know, how to describe them as polyhedra.
Yeah, I don't know what the obvious Euclidean metric would be.
So
okay.
I'll just add, at some point I had a conjecture that these things could be described as certain subspaces of standard simplices defined by algebraic equations. But I was never able to prove that you actually get a ball in those cases. But that would maybe be a way to get a metric, is that way. I don't know if that would be any use.
All right. Thank Nima again.
Thanks.